Please start.
Okay, thank you very much to Professor Kamada for chairing this talk and his kindness to control questions eventually at the end of my talk. So as you see the title, A Topological Approach to Turbulence Cascade, implies some physical background and, of course, the mathematics background, the second part being easier, considering that this is a conference in mathematics and not theory. This work started a long time ago, more or less 12 years ago, in collaboration with Professor Xin Liu at Beijing University of Technology in China. And he moved steadily, slowly but steadily, ever since, considering that the limited number of forces we have to work on this project. This project sounds unusual to mathematicians, but I have to warn you that this project is also pretty unusual to physicists. Okay, so be warned about this. The presentation goes as follows. We have four topics, key topics. One deals with the topological cascade of vortex tangles in superfluid turbulence, just to introduce you to the physics. Then we consider aspects of kinetic helicity and linking numbers of vortex knots and links. Again, maybe basic stuff in mathematical basic stuff in physical context. Then we move to application of knot theory, where I'll introduce adapted knot polynomials from field line helicity. And finally, I will hopefully dedicate the last 10 minutes of my talk to present you new results on topological cascade of fluid flows interpreted as geodesics in an appropriate knot polynomial space. Right, so let's start to consider what is well known to physicists as one of the most important open problems in classical physics, i.e. turbulence. Here we have a very famous drawing by Leonardo da Vinci, where there is a kind of rendering of what you may call the vortex structures. And ever since 1500 onwards, these posed very difficult questions to both physicists and mathematicians. Of course, progress was done, and the early days of 1900s, we have a little quote from Richardson, a meteorologist, that captures the idea that I want to convey to you. The idea is that vorticity goes from large-scale structures to small-scale structures, and then in real fluid, dissipative fluids, then they dissipate away. And the quote goes like this: big whirls have little whirls that feed on their velocity, and little whirls have lesser whirls, and so on to viscosity. This is a very famous quote among people working on turbulence, but gives you the idea of what we have in mind. Now, modern rendering of vortex structures in a turbulent classical fluid is here, provided by this picture. This is a snapshot of simulation, direct numerical simulations of the governing equations for real fluids, i.e. the Navier-Stokes equation. Now, from the 90s, we were able to focus on structures, on vortex structures, very closely. And you can think of these vortex structures as a bundle of vortex lines, as beautifully represented by this numerical simulation snapshot of vorticity. Now, of course, we can study these vortex structures forming, for example, knots. And this is recently done by the Hussein group from the year 2021 onwards. So we have a direct numerical simulation of the evolution. Remember, there is time here. The evolution of a trefoil vortex knot forming a knot through a process that in vortex dynamics is called reconnection. In other words, the knot strands interact, reconnect, change the topology of the system, providing different knot or link types, in this case, formation of a Hopf link, intermediate stage, and then two separated loops that then dissipate away. So you see that with time and through reconnection, we go from, say, a trefoil knot to unknotted, unlinked loops. Very beautiful work was done earlier on by providing a vortex trefoil knot evolution in water. So actually a real experiment of the formation of a trefoil knot forming at a certain point through reconnection, topological change, a Hopf link, and then a long evoluted loop. And then after this, through reconnection again, unknotted, unlinked, smaller loops till dissipation. I'm talking real vortex in water, and dissipation is because of viscosity of water. Now, the problem of reconnection has been known since the 50s, and here is a beautiful pictorial representation of the idea by Feynman, 1955, where in his lecture notes on superfluid systems, he draws the idea of an anti-parallel reconnection of vortex lines. And as you see, we go from a large loop to an ensemble of very small loops. I cannot resist to show you a typical example of this by the experiment done by the Irvine group in Chicago. You see here the formation of a trefoil knot in water, and is visualized by light bubbles, vapor bubbles. There is a reconnection here going on, forming a Hopf link, and then through a secondary reconnection, two distinct loops, and then final dissipation. This is a very famous experiment done, as I said, 2013, and reproduced in many ways by numerical methods. Why we focus, or at least I want to focus on superfluids, simply because superfluid turbulence capture the essence of the skeleton of classical fluid, of a real fluid, and superfluid vortices can be seen as a highly localized tangle of vortex lines. So vorticity is exactly where you see it. And so this is a very interesting way to study turbulence, because maybe we learn aspects of turbulence, superfluid turbulence, and one day the hope is to go back to export this information towards the study of classical turbulence. So from now on, I will focus on superfluid vortex tangles. Now, the vortex tangles I mentioned are, of course, given by localized field lines. And in a couple of years ago with Simone Zucker, we were able to reproduce the cascade of a trefoil knot in water by direct numerical simulation of the trefoil knot under the governing equation, in our case, specifically the Gross-Pitayevsky equation. So you see again, we started with one color, trefoil knot, and then through reconnection, the production of a Hopf link, and then one long unknotted, unlinked loop, and then further reconnections produce two distinct separated loops. So exactly this sequence. Very interestingly, because this was in parallel with a number of works on superfluid turbulence. And here is an example of one of the many that were done during the last 5 years. And this is a vortex tangle, and again, very complex network of filaments. And then through reconnection, these disentangle gradually through a number of reconnections to lead to an ensemble of unlinked, unknotted loops that then eventually evanescent or evaporate in space. The localization of vorticity in the tangle pushed people to consider aspects of topology. And so very recently, 3 or 4 years ago, was announced the spectrum of knots and links in the analysis of a vortex tangle. This was done by the group of Carlo Barenghi in Newcastle. They analyzed the vortex tangle in superfluid turbulence, and they were able to extract knots and links by using just the Alexander polynomial to detect the complexity of the knot. If we take the highest degree of the Alexander polynomial as a, say, sign of complexity, then they found knots of the order of this degree of the order of hundreds. So you can understand extremely complex knots that, again, in time, they evolve, interact, reconnect, and gradually decay to just loops and eventually disappear. All this provides us a background for work on this system by using, indeed, topological techniques. The analysis of the Cascade process was, during these recent years, was also done by different groups. I like to quote again the Willem Irvine group that under the Gross-Pitayevsky equation studied the cascade of the 6-2 torus knot to form a different type of knots and links, from the 6-2 to the link, and then the knot to the link and the unknots. And of course, under the appropriate governing equation, they found that the cascade was along different pathways. It's not unique because it depends very much on the initial conditions. And so different pathways occurred. And the question is, which is the most probable pathway among many? In very recent months, rather big work was concluded by considering the decay under the same equation, the Gross-Pitayevsky equation, of the Borromean rings. So here the initial condition is a Borromean ring, and we have again the most probable cascade given by Borromean rings going to whited link, reconnecting, producing connected Hopf links, and then again producing trefoil knots, Hopf link, and then unknots. Notice that the process is a kind of simplification process through reconnection that is generic process in all these situations. Again, the cascade is given by various paths, predominantly the one I described, but other paths are possible simply because of the different initial conditions, i.e. the geometry of the initial, in this case, Borromean rings. Okay, we are now at the stage where we can apply, as I said, techniques of knot theory to follow this process that is so interesting for physicists. Now, the proposed technique is based on use of a very fundamental quantity well known in fluid mechanics. So let me just very quickly remind you of what I will refer to. This is kinetic helicity. Moreau, 1961, proved rigorously that this quantity, the integral of the velocity times the vorticity integrated over the domain of the definition of vorticity is a conserved quantity of the dynamics. In other words, is a time invariant quantity for ideal processes. Now, I like to point out to you that what is important in this integral is vorticity. So the localization of vorticity in space-time. Indeed, because the velocity u is through B0 sub r expressed in terms of the global integral of vorticity. So if you think to substitute this term in the integral above, you see that this integration is depending entirely on the vorticity distribution. Okay, so this is our preferred quantity for fluid mechanics. Very well. And then we want to focus the case for superfluid tangles. In this case, vorticity, instead of being spread in the volume of the domain of the fluid, is localized, as I said, in thin filaments or vortex lines. And then we will consider these making knots and links. So imagine that our preferred tangle is made of a disjoint union of knots and links, and now, from now on, these knots and links are the physical knots and links where vorticity is defined. In other words, this volume integral can be reduced to a sum of line integrals defined on the so-called axis of each vortex knot, and we have to consider to make the dimensional quantities correct. We have to consider a vortex strength for each vortex. So phi I denotes the intensity of each knot and link in the tangle. There is now a bridge, a fundamental bridge between first principle of fluid mechanics and fundamentals in topology, and this is rooted in an original work by Moffat in 1969, and then kind of contributed with my work in 92, where helicity given by this integral expression actually along lines of vorticity can be expressed in terms of linking numbers, where LKIJ is just the well-known Gauss linking number between knot KI and knot KJ in the tangle, and SL is also topological invariant of the knot and is known as the Calugarianu-White self-linking number. From now on, I will focus on this quantity, and in particular, I will consider the case where, first of all, vortex strength of all knots is set to be 1, which is consistent with quantum vortices in superfluid case. So I can simplify this expression to this, which expresses very clearly the relationship between the helicity of fluid mechanics and the topological content of this quantity. And then for one single knot, then we have a unit strength, and then helicity becomes just the line integral of one knot, and is given here. So we reduce the linking number of Gauss to 0, and so the integral of UDL becomes simply the self-linking number of the frame knot. And from the Calugarianu's work of 1961, we know that self-linking number, I repeat, a topological invariant of an isolated knot, framed knot, can be written in terms of two quantities, the writhe and the twist. The writhe is the writhing number of a closed space curve. Please do not think of this right as just confound this right with the right of an oriented link diagram. Of course, the right of an oriented link diagram is derived from the writhing number of a space curve introduced by Fuller, 1971. And then the total twist number of the frame knot, which itself can be decomposed in terms of two geometric global quantities, total torsion of the space curve, and the internal twist of the framed ribbon placed on the knot axis. Okay, so we have this very interesting combination. The helicity is coincides with the topological quantity given by self-linking number, but this can be further decomposed in terms of two global geometric quantities, the writhing number of a space curve and the total twist number of the knot, which can be quantified, can be measured by numerical values through just analysis directly from data of simulations, or if we know the curve and the knot analytically, by analytical means. All right, so here I'll show you the application that we pursued with Xin Liu and myself. If K denotes a vortex knot of helicity H, given by this expression, E to H satisfies the skin relations of Humphrey PT polynomials of two variables A and Z, where now the dummy variables of A and Z can be expressed directly in terms of measurable quantities, total twist and the writhe. So in other words, A and Z, not only dummy variables of the polynomial, but now values, numerical values associated with the physical knot. Let's put this idea to a test. So we consider a sequence of, for simplicity, of a set of trefoil knots and links, and one single reconnection at a time makes this process topological complexity decreasing. So the assumptions are that all knots and links in this test case are elements of this class. The topological complexity is assumed to decrease monotonically by a single stepwise unlinking through reconnections, and the topological change occurs by a single orientation-preserving reconnection at a time. When we do this, we can express a recursive relation in terms of Humphrey PT polynomials, where starting from the original polynomial for the trefoil knot and the Hopf link, we can generate the polynomial for all knots and links in this set. Now, because I said writhe and twist can be computed analytically or simply from data, we can come up with these numerical values for A and Z. A, this number, and Z, this number. So when we plug in these numbers to our recursive relation polynomial expression, we get a monotonic decreasing sequence of values of the adapted Humphrey PT polynomial, which shows very well or at least represent very well, the cascade of the physical knots that we saw in simulations. All right, of course, we can reduce Humphrey PT to the well-known polynomials like Alexander or Jones. If we go to Jones, the two variables become one, and the one single variable can be quantified in terms of writhe. Okay, so we can put this in the context of a more abstract setting. Let's define the knot polynomial space in which we can compute our quantities. Knot polynomial space will be computed considering the topological change due to a single reconnection at a time, considering knots and links by Jones polynomial, standard Jones polynomial, and then we use the adapted Jones polynomials by using numerical values appropriate for writhe and twist, in particular writhe in this case. So each polynomial for the knot type will be represented by a numerical value. Numerical value for Hopflink, we have 138, for the trefoil knot 425, etc., etc. And of course, the unknot, consistently with the standard definition of Jones, is just number 1. Well, we can interpret this fact that knots, more complex knots, have an associated increased number and numerical value a la Einstein. So think that more complex knots are like weighing more because of the numerical value is increasing with respect to lighter knots or unknots that have just simple value 1. Well, instead of using this picture, I use basically the same idea to represent the complexity in terms of height functions. So we prefer a landscape, a mountain landscape, that sees on the peaks the more complex knots. And then because we have in mind a topological cascade towards unknots, we can think of geodesics along this metric space that leads complex knots to the sea of unknots. So the sea is represented here by the polynomial value 1. Okay, so I need to introduce now a metric space because we want to measure distances and in order to construct geodesics in this space. So I will define very simply a knot polynomial space as an n-dimensional discrete Euclidean space, and whose metric is given by complete set of polynomial values of orthogonal type that form the basis. Now, don't think of these polynomials as not polynomials. Think of this polynomial as like Legendre polynomial, Jacobi polynomial, that are useful to construct the basis. So suppose we take the Legendre polynomial here, and this is what I'm going to do in my next slide. I use Legendre polynomial given by the definition of the inner product as shown, and then I want to have an orthonormal basis, so I have to normalize this term in order to get my orthogonal basis. And from elementary algebra, I can use this statement: any polynomial, say Vn, think of this, of the Jones polynomial, for instance, that can be described in this fashion, expanding this polynomial into the first n+1 Legendre polynomial, and these provide complete basis for our metric space. Okay, so here we are. The polynomial Vnx is the Jones polynomial expressed or expanded into Legendre polynomial. We have the coefficient associated with this basis, and these coefficients, which are numerical values now because we use the adapted not polynomial, they provide the coordinates for this metric space. So we are able to identify each knot through this set of coordinates. So we can construct distances between these knots. Okay, so we go for a more complex test case of our theory, and this is taken by the DNA unlinking process studied by the group of Mariel Vasquez in UC Davis, and this is the publication. They consider the cascade due to the recombination through topoisomerases of complex knots, and they saw the happening of the 2,6 knot that goes down this route that, notice, has been analyzed already by us and others, and of course other possible pathways through composite knots and links, etc. So, as I said, I highlighted this sequence because they found that this sequence has the highest probability values to occur. We wanted to apply our theory to their results as a test case. So in our case, we have to define a reference distance. So we take the shortest distance as if the initial stage given by the 2-6 torus knot, torus link in this case, would collapse directly to unknots through a simultaneous, instantaneous reconnections. Okay, number of reconnections. And we take this distance as a reference distance. And then we can evaluate all possible pathways. We identify 17 different pathways. And for each pathway, we had to compute the relative distance with respect to the direct cascade D0. So by doing this, we define a relative deviation, and from there, in a very simple manner, we introduce the probability associated to each deviation. Now, these red numbers are our numbers. The probability to decay to the unknot along this path, as you see, is dominant, and so is the optimal cascade, the optimal pathway that is the one we already investigated using Humphrey PT, and comparative results with the group of stalls points out that we are doing pretty well with all numbers that we considered. So our technique seems to be very promising. So I'll use my last 10 minutes now to show you the new results from there. So from 2020, very few people helped us, a number of students, but not so many. And so we moved, as I said, rather slowly. And the work I'm going to show you is just work in preparation. So imagine that we define the topological complexity. As you know, we have many definitions of topological complexity in knot theory. Here we have one that we proposed in 2020. And according to this definition, in this diagram, you see all the cascades that we discussed so far. So, for example, this is the dominant cascade of Stolz and Tau that we reproduce, and others, all towards the unknot. Okay, in this axis, we have this topological complexity chi, and along this axis, horizontal axis, we have knot types. Now, first question, can we extend these to other knot types and see knot polynomials and see how they go? Well, this is an easy question, because if we consider Alexander-Conway polynomial as Jones is a reduction of Humphrey PT, Alexander-Conway is a reduction of Jones, so expectedly the use of adapted Alexander-Conway polynomial didn't bring us new results other than confirming that the typical pathways we found are similar in numbers. Okay, what about the different bases? What about using different type of polynomials for the bases other than Legendre? So we went for Hermite polynomials, and again, no much difference with Legendre. So that means there is something strong behind in the theory that we are proposing. Next step is that the computation of all possible knots and links, including composite, up to 6 crossings. So we are now extending the first results to a more elaborate set of data with 26 crossing knots examined. And here we have the new results, and you start seeing kind of 2 distinct islands. The former results given here are part of a rather enlarged pink island, and the new island in light blue becomes visible. When we went to the next step, we wanted to examine the all knots and links and composite up to 7 crossings. By this approach, we determine 34 knots of these types, and the islands are still quite well separated, and all previous results encapsulated in this new result. Now we are at the point where we can identify these 2 islands more clearly, and I will say that the first island, the pink color island, is the island that includes all positive or negative powers of the Jones polynomial. So the Jones polynomial here represents a kind of strong chirality present in our sets of knots considered, whereas the light blue region includes mixed positive and negative powers. So we call this region a region of weak chirality for knots and links. Can we extend this further? Well, all this now has been done by hand, and to 8 crossing, I tell you, is a lot of work. There was a student who worked on this for almost a year, hand by hand, going through 129 8 crossing knots, remember composite knots included, and the 2 islands remain well separated. So this is as far as we could go so far. So this is the work that is in preparation, with, of course, lots of information that I have no time to discuss here. What I want to do is to use my last few minutes to tell you where we're going with this. Well, as I told you, the idea started with a meeting with Xin Liu long time ago when I was a Scuola Normale in Pisa, 2011, and the proposal was how about to use knot theory and topological approach to study this big problem of turbulence, at least for superfluid quantum vortices. So the work is, first of all, to extend our technique to 2 variable polynomials. We didn't do it so far because the basis we need, the Legendre, Hermite, Jacobi, whatever basis we like to use, is more generally defined for polynomials of a single variable. So we have to fish polynomials of differential equations in 2 variables to see how to apply this approach for example, Honfley PT. So we are working on this right now. Relate topological cascade to information entropy. By information entropy, I mean, really technically speaking, the mathematical entropy, so Shannon theory. And this is also very fascinating because, of course, we have to define a new type of entropy associated with the information that, so to speak, we lose, or better, gain, technically speaking, when a complex knot goes from some complexity to a lower complexity. And of course, the long-term dream is to relate possibly this topological entropy to energy cascade, and so the energy decay in the process. All this, if we'll be successful, will form a kind of topological approach to superfluid turbulence, and maybe one day to a classical turbulence, but this is still a long-term aim or goal. Within this context, and closing of my talk, I am amused to present you a kind of revisit of Richardson little rhymes. So instead of this dynamical view, which is still very good and appropriate, I propose a topological view, i.e. big knots have little knots that feed on their topology, and little knots have just knots that disappear into vacuity. With this, I thank you very much for your attention. Thank you.